Good morning, everybody. So we're going to continue our lecture with these new topics, new chapters, chapter 4. The topics for chapter 4, the main topics will be on potential difference and energy density as can be obtained from the course information. Okay, so we have these topics here, potential difference and also the energy density. So for this lecture number 8, our concern will be on the topics of introduction to the concept of potential difference and also on the absolute potential. Okay, lecture number 9 will be covering the topics of energy storage, gradient, okay, and also the energy within a system of charges. So that will be our main topics to be learned in chapter 8. Okay, so this will be the main topics in lecture 8. There are two topics to be learned. The first one is on potential difference, okay, and this will be followed by the absolute potential. So in short, we're going to understand what is potential is all about, yeah? So reference for this book, for this topic can be obtained from Sadiku. This is the reference chapters, the reference pages for this lecture number 8. So motivation for this lecture is to enable the students to understand, yeah, the concept of potential difference and also absolute potential, which are said to be induced or produced by the point charge and also the continuous charge system, right? So we're going to see what should be the potential produced by the point charge and also other type of charge distribution, which include the line charge, the surface charge and the volume charge. So basically, this is the important things to be learned in chapter 8, lecture 8, yeah? Okay, so objective for lecture 8, number 1, by the end of this lecture, you must be able to understand what is meant by potential difference and also what is meant by absolute potential or potential in short. And number 2, you must be able to calculate what should be the potential or potential difference induced by the point charge or point charges and also other type of continuous charge structure. Okay, so that will be the objective of lecture 8. Okay, so before we can proceed with a potential, it is good if we can understand the definition, the concept of work in electric field. Yeah, because work and potential is interrelated between one another. Okay, so we are having, for example, sir, if we consider that we have a point charge Q, and the charge Q is said to be moved from a point of B to the point of A. Yeah, so that should be the movement of charge Q, and we assume that within this movement, there is an electric field intensity E, yeah, which is exists, yeah, which are said to exist in these particular conditions, yeah, in which we can see that the point charge Q is said to be moved from point B to point A in the existence of the electric field. Okay, so in this particular case, there should be external work which need to be done, yeah, by the charge Q, or can we see that external work is used to move, yeah, external work is used to move the charge of Q from the point of B to the point of A in the existence of the electric field. Yeah, somehow we are saying that there is external energy or external work that will be required to move the charge Q in this existence of the E field. Yeah, okay. So we can say that this work that will be required in order to move the charge Q, okay, along the length of L. We know that the definition of work is the force multiplied with the distance, right? So we can see that a small work, which is defined to be a dW, the dW will be equals to negative F dot dL. Okay, why use negative here? Because we are saying that the external work has been used here. Yeah, that's why we use a negative sign to define the external work that has been applied in moving the charge Q. Right. So for this particular case, that should be the small amount of work that will be required. And the work is in having units of joule. So with that, we can straight away calculate that the total work that will be needed in moving the charge of Q from the point of B, yeah, to the point of A in the existence of the electric field can be obtained by simply integrating the dW, okay, in which we're going to have that the W, the total work, will be equals to the integration of dW, which will be the integrations of QE dot dl, yeah, because we know that F equals to Q of E from our understanding of the Coulomb's law, yeah, in chapter 2, and the integration will be from the point of B to the point of A, yeah, from point of B to the point of A, because we are moving the charge from point B to the point of A. So that should be the amount of work that will be required, yeah, the external work, yeah, to be exact, will be the external work that will be required to move a charge of Q from the point of B to the point of A in the existence of the electric field E. Okay, so that should be the definition of the external work or external energy. Okay, so from the equations that we have defined just now, where if I can rewrite it for you here, we have W will be equals to integration negative of QE dot dl, yeah, integration from the point of A, the initial point to the end point of A. Okay, the dl here will be depending on your coordinate applied or coordinate used, yeah, and we have learned this in lecture 2 or chapter 1 of EMT on the revision part, where the dl is defined to be this equation for the Cartesian, cylindrical is defined to be like this, and for spherical to be is defined to be look like this, yeah. So this has been learned in lecture number 2 before. So depending on your problems, yeah, depending on your given problems, you need to adapt or you need to adopt the actual the proper DL to be applied in solving the given problems, yeah. Okay, so let's have a look at this example here. We are having a path which is connecting 3 points, which is we have a point of 200, we have a point of 040, and we have a point of 004. And the path is defined to be path number 1, yeah, from 200 to 040. And then we have a path 2, which is connecting the point of 200, yeah, that should be the point of the second path, yeah, 200 to 004, and 004 back to 040. So we have path number 1 and we have path number 2. Okay. The thing is that the question asks us to find what should be the work done in moving a 2 coulomb charge in the existence of this electric field intensity E, which is given to be in general form of x direction of x plus y direction of y plus z direction of z. If we are taking the first path from 200 to 040, we are defined to be this labeled to be this path number 1. Okay, and then what should be the total work required in moving the 2 coulomb charge from 200 to 040. Basically, it's the same starting point and the end point, but we are using different path now. Yeah, path number 2. Okay, along path number 2, and the third one is what should be the round trip movement. Okay, never mind. Let us proceed with number 1 first, which is the movement of charge of 2 coulomb from 200 to 040 by using path number 1. Okay, so let us proceed with this calculation of work. So from what we have learned previously, we have defined that the work in the electric field intensity existence, I mean within the electric field intensity value, we're going to have that the W will be defined to be negative integrations of QE dot dl, okay, where we have the Q will be equals to 2 coulomb, and electric field is defined to be x direction of x plus y direction of y plus dz direction of z. Whereas the dl will be depending on the systems of coordinate, as I mentioned in the previous slide. So looking at these problems, it can be said that we are dealing with the Cartesian system of coordinate. So the dl shall be then defined to be dx direction of x plus dy direction of y plus dz direction of z. And further on, we can rewrite this equation to be -2 integration of x dx, okay, plus integrations of y dy, because this is a dot product, plus integration of z dz. Okay, so let us put the range of integration for the x, y, and z. So we have to be based on the point, yeah, and on the point, the starting point and the end point. So we are starting from 200 to 040. So for that, the x will be having a range from 2 to 0 as given in the point here. So it should be from 2 to 0 for the x range. Y will be from 0 to 4. Yeah, the movement is from 0 to 4. Whereas for z, there should be no changes at all because the point, the starting point and the end point for the z are the same. Yeah, so 0 to 0. So it can be said that the z integration can be cancelled out. So left only with the x and the y integration. So we can write that the work will be equals to -2, yeah, -2, okay. Um, okay, -2, and then we have x squared over 2 from 0 to, so from 0 to 2 to 0, and then we have y squared divided by 2 from 0 to 4. So if we proceed with this substitution of the values, we are supposed to get -2. So that should be -2 plus that should be 8. And the result for this will be equals to -12 joule. Yeah? So that should be the work, the external work that will be required to move a charge of 2 coulomb within the existence of electric field E here. Okay? Okay, so that should be the work that will be required, yeah? Okay, so this is the external work, yeah? That's why we have a negative sign there. External work will be required, right? So let us proceed to the second part of the questions, which is to find the same work of 2 coulomb, moving a 2 coulomb charge with this E field existence, but now we are using different path, which is path number 2, from 200 to 040 using path number 2. Okay, so for that, we are supposed to get the W using path 2, but root number 1, and that will be root number 2, yeah? Okay, so the total work will be equals to negative uh, integrations of QE dot DL. So we can define it to be equals to integration for root number 1, yeah, plus QE dot DL using the root number 2. So that should be a summation, yeah? A summation because the path 2 do have 2 roots, yeah, 2 roots, roots number 1 and roots number 2. So we have to add them together so that we can get the total work in moving the charge from 200 to 040, yeah? Okay, root number 1 is a movement of charge from 200 to 004. So that can be defined to be negative of 2 integrations of x dx, yeah, plus integrations of y dy, plus integrations of the z dz, in which the x is a integration from 2 to 0, yeah, for root number 1, y should be no changes at all, whereas for the z, it's from 0 to 4. So that should be root for, this is for root number 1, yeah, so that can be equate to 0, can be equal to 0, whereas for the second integration, root number 2, that should be -2 integrations of x dx plus integrations of y dy plus integrations of y dy, that should be z dz. Okay, x is a change from 0 to 0, no changes at all for the x, yeah. Yeah, this is root number 2, yeah, from 004 to 040. Y will be from 0 to 4, whereas for z will be from 4 to 0. Okay, so it can be said that for the second integration here, for the root number 2, for the x will be no changes, yeah, no effect of the x integration. So if we can proceed with these results for the work total, so that will give us negative 2, integration for that will be equals to x squared divided by 2 from 2 to 0 plus z squared divided by 2 from 0 to 4. Okay, that's for root number 1, plus for root number 2 will be negative 2 integration of y squared over 2 from 0 to 4 plus z squared divided by 2 from 4 to 0. Okay, so that should be a summation of the total work. So from here, we can see that for the second root, yeah, this part and this part will be cancelled out, yeah, because numerically it can be shown that the summation of these two values will be equated to 0. So we can ignore the second path contribution or second root contribution. So we're only left with this first root value. So if we proceed with that, we're going to get a WT or total work will be equals to negative 2. So that will give us negative 2 plus 8, yeah, in which the answer for that will be equals to negative 12 joule still. Okay, so which means that um, if we consider a second path in which the charge need to pass through or need to follow route number 2, charge have to move from 200 to 004, and afterwards it need to move from 004 to 040. Okay, so for the first path, it has been obtained that the total work is equal to negative 12 joule, whereas for the second path, okay, it also been approved. We have proved that the total work is also equals to negative 12 joule. Okay, what is the things that can be deduced or can be concluded from these results? Okay, it can be shown that based on this calculation, if we have a same initial point or starting point, and if we have a same final point, yeah, same initial and final point, it can be said that the total work will not be depending on the path taken. Yeah, as long as we have a same initial point and same end point, the total work will be the same, regardless of the path taken. So that should be the first conclusion that can be made from this exercise. Yeah, right. So from the first and second question just now, we have proved that the work is not dependent on the path taken. Yeah, it just depends on the initial point and the end point. Okay. Number two, point number 3 is need to calculate what should be the round trip movement at 200 along path 1 and path 2, which means what should be the total work that will be required in moving the charge from 200 in a round trip movement, which is a movement from the initial point and back to the same point. Yeah, so it means that we are moving from 200 to 040 and then go to 004 and back to 200. So that should be the movement or round trip movement. So from here, we can say that if a movement from 200 to 040 is negative 12 joule, so if we consider a movement the other way around, which means that we are moving from 040 to 200, it can be said that the work will be a positive. Yeah. So for that, if the work for path 1 is negative 12 joule, okay, 12 joule, we add with the movement, with the work required, if we move a charge from 040 to 200, we can get a positive charge, a positive work. And the value for the total work that will be required for a round trip movement of a charge 2 coulomb at 200, then the total work will be equal to 0 joule. Okay, so which means that there should be no work is said to be done, yeah, in moving a charge in a closed loop environment, in a closed loop environment. So which means that if we have a single point of A, we bring a charge along the path here and we go back to the same point, it can be said that the total work done will be equal to zero, which means that there is no work done. Yeah. Okay. So that is what we have conclude. Yeah, from these example. Okay. So this can be further written here. Okay, that is what I have mentioned just now. From the first observation that the work does not depend on the path taken, as long as we have the same initial point and the same end point. Yeah. The second observation is that the total work that will be required in a closed loop movement will be equal to zero. So from the equation just now, where we have W as a negative integrations of QE dot dl. This is from the definition of the work in moving a charge, yeah, that we have learned in the previous slide. So if we consider a closed loop movement, which means that we are dealing with the a closed loop integration like this, and if we can bring the skew to the left hand side, so we are supposed to get this kind of equation in which the work per unit charge will be a negative closed loop integrations of E dot dl equals to zero. Okay, so this is what we meant as the work per unit charge. Yeah, the work done per unit charge. Yeah, work done per unit charge. Yeah, and it has been proved that the total work per unit charge in a closed loop environment shall be equal to zero. Okay, so this equation, yeah, which is closed loop integrations of E dot dl equals to zero, is defined to be a second Maxwell's equation for a static field. Yeah. Okay, so please be noted that the equations here, I mean the work in a closed loop that we have defined in this slide is strictly applied only for a static field. Yeah, strictly applied only for a static field, which means that the E field here must be a static field. Later on, in chapter 8 or chapter 9 or chapter 10, afterwards, when we are dealing with a time-varying field, where we have the E is defined to be time-varying, yeah, ET, time-varying. So these equations of E dot dl closed loop integration equals to zero is not valid anymore. Okay, it's not valid anymore if we are dealing with the time-varying electric field. So this equation, as I mentioned just now, is strictly applied only for a static field. Yeah. So this is defined to be the second Maxwell's equation, which is a continuation extension from the first law of Maxwell that we have defined in our class last week, which is based on the Gauss law. If we can refer back to lecture 7, where we have d dot ds equals to the enclosed charge. Okay, so by assuming that the volume of your Gaussian surface is approaching zero, so we have defined this equation to be divergence of d equals to rho v, and this is what we define to be a first law of Maxwell. Yeah, so this is what we have learned in lecture 7 last week. Okay, so this is second law of Maxwell. Yeah. Right. So these are the important things that we have defined from the exercise on these, on the examples previously. So the first one is the work done does not depend on the path taken. Yeah, which means that if you have a point of A and B, this is A and this is B. If we choose path number 1, if we choose path number 2, if we choose path number 3, if you choose path number 4, as long as you have a initial point and the same endpoint, the total work will be same. Okay, so that is the first observation. The second observation is based on the second law of Maxwell, that the work done in moving a unit charge in a closed loop movement will be equal to zero. Yeah, right. Hopefully you understand this clearly on the concept of work. Yeah. Okay, so let's have a look at this example here, where we need to obtain, we are given the E field. Yeah, we are given the E field here, where the E field is defined to be 2x, y, z, direction of x squared z, direction of y, and x squared y, direction of z. Okay, the question is calculate the amount of work that is necessary to move a 2 microcoulomb charge from 211 to 512. Okay, so again, we are dealing with the Cartesian system. So we can straight away use the equation work that it is defined to be negative Q integrations of E dot dl. Yeah? Okay, so for these examples, we can say that, okay, the charge is negative 2 microcoulomb. The E field is defined to be 2x, y, z, direction of x. Okay, and we have plus x squared of z, direction of y, plus x squared y, direction of z. And the dl shall be further defined to be dx, direction of x, plus dy, direction of y, plus dz, direction of z, yeah, because we are using the Cartesian system. So this can be further written to be negative 2 micron, integrations of 2x, y, z dx, plus integrations of x squared z dy, plus integrations of x squared y dz. Okay, yeah? Right, so let us proceed with this integration one by one. Okay, we have a point here, yeah? The point, the movement of charge is from a point of 2, 1, negative 1, and it moves to this particular point of 5, 1, 2. Okay, right. So that should be the point of interest, in which we can see that based on this movement, the x is moving from 2 to 5. Yeah, it can be said that x is moving from, yeah, for the x is moving from 2 to 5, the changes of the coordinate. For the y, it is changing from 1 to 1, no changes at all. Whereas for the z, it is from negative 1 to positive 2. Okay, right. So let us look at these examples here. I mean, we look at these integrations here. We have for the work, yeah, for the first one here, right? We have a negative 2 micro coulomb, and we have a, for the x, yeah, for the dx integration, we have a 2. Okay, we have a 2, the x should be there, whereas for the y we have a okay, let's have a look here. Okay, never mind. Regarding this point, if we move from 2 1 negative 1 to 5 1 2, it can be said that we can move initially from 2 1 1, okay, to the point of 5 1 negative 1. Okay, that should be the first path taken, yeah, because we have defined initially previously that the work does not depend on the path taken, yeah. So what we did here is that we are moving in the x range first, in which we make a y and z to be a constant value, yeah. So for this, you're going to have integration for a x range difference, yeah, which is from 2 to 5, whereas the y and z values are made constant, yeah. So for this, we base on this first integration here, we're going to have a x, yeah, y can be defined to be negative 1, sorry, positive 1, yeah, y is positive 1, whereas z is negative 1, and we have a dx integrations then. Okay, so we're going to have the integrations will be equals to, I mean, the x will be having a range from 2 to 5, yeah, 2 to 5, right? And then we can define that for the second integration, in which we are dealing with the y changes, y changes, we can see that there is no changes for the y, yeah, no changes for the y, so we can be said that that for these integrations of dy, it will be 0, yeah, because no changes for the y uh, value, yeah. Whereas for the z, we can have a changes from -1 to +2. Okay, so from for this range, x will be having a same value of 5, y will be having the same value of 1, whereas z will be having a change from -1 to +2. So we're going to have then the integrations of x, which is 5 squared, okay, plus y, which is 1, and then we have a dz, and the range of integration for the z will be from -1 to +2. Okay, so that's how we define the range of integration, or that's how we define the work that's required. Yeah, so what we did is that we segregate the point. Initially, it is from 211 to 512. So what we did here is that we are taking another route, but we are dealing with the same initial and end point, but we took another route just for the sake of simplify or make the integration easier to be calculated. Yeah, so that's the reason why. Yeah. Okay, so we proceed with the integrations here. So I'm going to do it here. So we're going to have W will be equals to -2 microcoulomb, and then we're going to have a 2, sorry, negative, yeah, negative sign should be there. Negative of 2x squared divided by 2, which is from 2 to 5, plus, sorry, this is y, 5 squared. This is no, that's no plus here. I think I made a mistake for this integration. Sorry for that. Okay, so that should be 5 squared times 1, supposedly, yeah? Okay, so that should give us 25, yeah, 25, and z squared, sorry, z, yeah? Sorry, z, that should be z only, which is from -1 to 2. Okay, so that should be the integration. So we can calculate it now. So we're going to have -2 microcoulomb. So that will give us -2, 25 divided by 2 minus 4 divided by 2 plus 25. So that will give us 2 plus 1, which will be equals to 3. Okay, so the work will be based on this value, -2 microcoulomb. 21, with that will be equals to -21, plus that should be 76, and end up going to have W should be -2 micron multiplied with 54, and end up going to have the value of -108 microjoule. Okay, so that should be our work that will be required in moving a 2 microcoulomb charge from 1 -1 to 512 in the existence of this electric field intensity value. Okay, yeah? Hopefully you understand these examples clearly. Again, we are still in the topics of work. Yeah, topics of work that will be required in moving a charge from in moving a charge, yeah, in the existence of the electric field intensity. Okay, so we're going to continue lecture on potential in part 2 later on. Yeah, thank you very much.